like to go back to modularity because that's one of the crucial features that many of these systems we're looking at have, but that's not really been discussed a lot, with the exception of if you knew what you're looking at, PVS, or Sam was showing us to it. But I would like to drill in onto this. And I'm not sure if this works. Yeah, this is coming. So we all understand and appreciate object-oriented development. Why? Because it allows us to...
I not appreciate object-oriented.
Okay, good. In some moral way, maybe not the way that Java does it. What we all do is modular development, meaning kind of separating out causes, making the smallest possible contexts in which we prove something and so on. And that's something all of you have seen, and you've all seen things like, starting with magmas, just a group, a set and an operation, adding the semi-group axioms, which is essentially adding associativity, then going to monoid groups and so on. And that's really what is also being done in lots of, say, computer algebra systems. The one thing where I've seen this is GAP. GAP is a very prominent computer algebra system. They do object-oriented development, but they're doing it in a slightly naive way. Namely, they have, they're a group and ring theory-based computer algebra system, and they have something they call additive groups, right? And they also have multiplicative monoids. Okay, so which means in the case of a computer algebra system, they have these huge towers of code which are identical, except that in additive monoids it's called plus, and in multiplicative monoids it's called times. Giant identical developments just via renaming. It's a, you can imagine, nightmare. And the only reason is that they can't do inheritance via renaming. So what we really want to have is something like this. You have a shared development of magmas and semigroups and also monoids, and then you kind of incorporate the additive part into ring via renaming, and the multiplicative part via renaming. Every composition here, the operation here, is renaming to multiplicate and to times, and you can already see that we're doing deduplication. So in a way, it's inheritance on steroids. Okay? And all of you know, I don't have to remember, when you can do these kind of duplications kind of multiply, and then you get exponentially much things. So I've told you we're in love with theory graphs. Essentially, theories as context. They contain objects and their properties in the form of axioms, and we have inheritance going on. Normal inheritance, those are the hooked arrows, basically identify everything that comes into a theory via two ways, whereas this kind of inheritance, which we call structures, other systems have various forms of those things as well. There, we actually don't identify. In here, we don't want to do that because the operation that comes up in two ways into ring, one time is called plus and the other time is called times, and we do not want to identify them. Okay? So modularity is important. We want to have different ways of doing that. And the good thing is that whatever holds here, for instance, that addition is associative, kind of also holds or continues to hold via all of the via all of the arrows. I said, I'm going to in a little bit more detail because I think that's one of the things that I do not want to discard when I'm going flexiformal, at least for the application of education. On the contrary, I think these kind of arrows are prime teaching targets that at least our stronger students actually somehow get when we're teaching them, even though we're not really helping them. And it's kind of like, I remember from school when we were doing gymnastics, we were always, we had this, I don't even know how it's called, and this
bars.
The bars, right? And the teacher said, wobbly wobble, and then said, now you do this. And I could never do this, because nobody explained me where the center of gravity was going. But once I got a teacher to actually explain it to me, I could do it. Okay? And when we're doing these kind of things in teaching, it's like gymnastics, where we're just, the teacher says, watch me do it, and we don't explain. I would like to be able to explain, and I think these theory graphs are a way of actually making things modeled so that we can actually explain. Okay, so we have these structures, but we have more in theory graphs, which is going to become very important. Another kind of arrow, and where these kind of arrows are, in a way, definitional, you make ringing by essentially copying all the axioms and objects over, right? So everything that holds here holds in ring as well, because we're basically virtually copying over the axioms via renamings. In these squiggly arrows, which we call views, we are making sure that all the, in this case, say, monoid axioms are provable in the integers. So instead of having kind of definitional links, we actually have interpretations between existing theories. That's nice. We give up the, we can also give up the condition of acyclicity that definitional links have to have, and we add all these kind of views, and these views have the same properties that all the arrows have, that all the, we call them theorem morphisms have, is that they're truth-preserving. After translation, everything that holds here becomes a theorem there. And these views, these interpretations, and again, many systems have something like them, can be used to model lots of things in mathematics, right? Views and composed with them any other theorem morphism are how notations travel. They're how theorems travel. These views, I've put in a couple. We have an endo view. They're perfectly fine. If you just, in a monoid or group or whatever, if you exchange the arguments, everything still holds, right? And if you remember that theorems travel by these views, then you've actually seen those. Very often in algebra, you have this, oh, this case follows from the preceding one by symmetry. What happens here is that you have a proof of the previous case, somewhere there. You move it, let it travel once around this view, and it's the same by symmetry. So this is not something that is rocket science or magic. It's just we can explain it. It's just movement of objects along views. That's something that's very important. Other things you may have seen are actually views. If you read the views in the wrong direction, they become examples, right? We have a view from monoid to the integers. The integers are an example of monoids. We can compose or build up views in stages, right? For instance, this view, basically we can build up by taking this one and mapping it to essentially that mapping this structure to that view. Right? So there's a calculus about views that allows us to not prove things multiple times. So, yes?
Just ask a clarification question. So things like ring there,
Yes.
I should think of that as a theory.
Yes.
And then integers is also a theory, so should I have in mind something like an integers together with enough axioms to pin them down? Like
Yes, absolutely.
Okay.
So, think that there's something down here on the theory graph, which
I something that says that will let me understand that there are positive and negative integers.
yes, both of those behave like natural numbers, and we have addition having the recursive definition. Yeah. Kind of the monoid axioms, you can already see how to prove them, like the monoid axiom for plus is actually the base case for the definition, recursive definition of plus.
Yeah. I have one more question. So I could say that the integers are the initial ring.
Yes.
Some such. So my theory of integers is going to mention all rings.
If you do it like that, yes. If you do it elementarily, like Peano did, then you don't.
Well, you could have there is a view in the other direction, right?
Yes. I'm just keeping it extremely simple. Right? There's a lot more you can do with these. This is what a normal mathematical audience immediately understands. And many of those things, if you have more of those, the bushier the better. Right? So you have lots of things. By the way, if these theories are logics, which is perfectly fine, then views into ZFC and so on are just the models. And any kinds of models are naturally views. And so there's a lot of things you can do with views in the formal setting. Yes?
Wait, so when you say that like integers are an example of a monoid, you aren't proving that there are such things. This is more like an axiomatization of the integer, and you aren't proving that that axiomatization is consistent, right?
Oh no! We never prove that something is consistent, except by exhibiting a view, no, I have to be careful, out of it. Into it. Okay, so, no, we're not assuming that, we're not proving consistency. And you can write down inconsistent theories, even in the formal MMT thing, but if you have enough views, then you can see that certain things are
So what you would call a construction of the integers is something like a view from the ZFC
yes.
theory to the integers?
Yes, so we have these foundational theories, and ZFC is one of those, and then you can view into them. And it's just a reformulation of the ideas that you all know.
But then you could ask if, at the same question, are you assuming that ZFC is consistent or whatever?
No, this is a purely proof-theoretic system. What you believe you're seeing is your private thing I would never pry into. Yeah?
I was trying to understand views as models, but then you said something like, if you're in ZFC, then view as a model.
No. A view into ZFC
Right, okay.
is a model.
So I don't know what a view in general.
A view in general is just a mapping from all the concepts of the source theory into terms of the target theory, such that every axiom in the source theory becomes a theorem in the in the target theory. That's what I would tell mathematicians. Type theorists, I would just say, well, it's just it's a well-typed homomorphism from the source theory into the target theory, and if you assume a suitable version of the Curry-Howard isomorphism, then that's exactly the same.
So, for example, there doesn't have to be a model because there's endo views. If you have a monoid, then you get the odd monoid. That doesn't assume that any monoids exist.
Oh yeah, absolutely. So if you have to have models, you have to have a view into some kind of a foundation you personally believe in. And some people believe in ZFC, and some people believe in topos theory, and what you believe is your private, your private thing. We're just giving you the machinery. And all of this is implemented, and you can ask the system the crucial questions, which we do. Okay, any more questions? One little thing about about these implemented, about the implementation in our MMT system is that you can think of this, you can think of views and structure as being giant copy machines, right? Whenever you have two theories that are connected by a theory morphism, you can take everything that's here and move it over there. That's what we do in math quite a lot. If you think about Fermat's last theorem, what's happening, there was somebody, Wiles established a view between modular forms and elliptic curves, and I always forget in which direction it points, and then he basically takes the huge and well-known theory from the one end and pulls it over the view and kind of hits the theorem via a view. Any structure theorem is a view. And that's one of the most important things we do in math, and we are so brainwashed into doing this that we even don't see that we're doing it. Think about all these little views between, say, sets and their characteristic functions, which we apply without even thinking. All these kind of little things. And we want to make them explicit in our theory graph. And the little invariant that we're keeping is that if this is a big copy machine, then you have kind of a core that you write down in your system. And you have a huge, or often big, set of induced knowledge. Right? Everything that you've copied but never written down. And one of the crucial invariants that we're keeping in our MMT system is that all of the things that are in the induced knowledge space have an MMT URI, which is kind of a fancy URI-shaped name, that has the property that if you know the represented core and you know the MMT URI, you can actually reconstruct the shape of this object. Think about what's here. From monoid, you get an axiom of associativity in the integers, and if you know that you're actually using this view and you know the associativity axiom of monoid, then you can make automatically the one in integers. That's very nice for algorithms because you never need to actually remember the shape of these. You can make everything incremental because you can always replace things by their name and incrementally expand or lazily expand as much as you need. That makes many of the algorithms tractable and logic independent. Yeah, one.
So yeah, the URI resolution depends on the core, right?
Oh, absolutely. If you don't have the core, you're sunk.
It probably refers to the core. I mean, take that and whatever.
Yeah, you can think of a morphism as a set of definitions, and then there's a definitional expansion. So no big.
URI is a kind of term in the meta level that tells you what.
That's what you can think of it. It's slightly different though, but yeah, it's an assignment.
Is it monotonic? If I change the core by adding stuff.
Yes.
You just gain new URIs. But
yes. Okay. You gain more stuff up here, but the invariant is that you can still reconstruct all of the induced things. That's the important thing, and that's something I would like to use later.
Sorry, I also had another question, which is, before you said that the views, they preserve truth.
Yes.
I guess in the sense of like the typing judgments.
Yes.
Of the declarations.
And of course, the proving judgments, if you
But
have
you
it.
said that proofs are not important to be formalized.
No, I think they're not the only thing that is important. Proofs are important to all of us, of course, in more ways than just the ones we have here. Proofs are things that are educational objects that we tell us why certain things are true. Just thinking of proofs as certificates, I think, is misguided. Spending a lot of work, 20 person years of doing the next after 5 successful huge theorems. I'm questioning whether that's actually going to be good, but I like the work. Lots of Teflon pans. I just won't do it myself because I think it's a waste of time. But that's, for me, it would be a waste of time. Who knows what you're doing? Okay? Good. So, this is the typical thing. This is elementary algebra, the same thing in a little bit more detail. And there are lots of views and so on that are missing, but you can see that we have a big copy machine. And the important thing is only that this one I'm underestimating. This induced knowledge space might actually be infinite. You have cycles. So, the key lesson I want to show you is that STECH is re-implementing the essential parts of MMT in LaTeX. And that's our goal. Everything in STECH, which is just essentially a LaTeX package, which is minimally invasive, which means we can kind of put it into any other class. You can do it and put it in LLNCS, you can put it into good old article, you can put it everywhere. It just basically adds invisible semantic annotations that turn any of your papers into one of these. And I claim that's a huge advantage. And I want to show you some of the things you can do that. It's a RustTech package, it's on Tech Live, so you all have it on your machine already. And we basically make it MMT equivalent so that we can actually harvest the formal part into MMT and get all the crunchy theory graph goodness. We have a big set of documents. We have kind of course materials and slides about the worth of 3,000 pages. We have a set of we have a mathematical library with something like 2,500 concepts, of which I think 1,500 are in multiple languages. So we have a lot of experience, and we're using it in education, which is what I want to know. Okay, so what does STECH look like? There's 2 central concepts that are borrowed from MMT. One is that we have these symbols. Symbols are the mathematical concepts that have an MMT URI. And those are the objects we're kind of throwing around. Think of the plus in a ring as opposed to the times in the ring and so on. And we need to sprinkle that information over LaTeX. And for that, we are using semantic macros. What are semantic macros? There's things like nat plus takes a sequence of arguments, and many, and looks in the end like A plus B plus C, ink on paper. And internally is disambiguated into apply the nat plus function to a sequence of arguments. So we basically have the formalization at the same time as it looks good in PDF or in HTML or something like this. So you basically want to have these 2 outlets, the formal part, or the partially formal islands, and looks good on paper. Okay, so how do you do that? Well, let me show you in a simpler example. You declare a symbol nat for the natural numbers. It has a system name, natural number. And it introduces a semantic macro NAT. In the second step, which can be combined into one, of course, is that you define a notation declaration that basically does the usual thing. It gives NAT the notation math boldface n. Right? The double struct n we all know. You can have multiple of these notations, you can distinguish them, and you can actually choose which one is going to be your default notation. You can write down things like backslash NAT in the French notation, which I'm making up at the moment. I think French uses the same one as we, but if I had a notation for French, then I could just use that in any of my texts. If only to say, well, the French have a weird way of writing binomial coefficients or something like that. Yes?
So I'd like to ask a silly question. So what and where is, how do you store the definition of that? Because the obvious thing is if you give this to a computer scientist, they will say 0 is in the natural numbers, and if you give it to a mathematician, they will say it isn't. Yes.
There is a special definition environment for those. You mark up the definiendum, the thing that's to be defined, and what it is defined as. Yes. So we combine symbols, definitions, maybe axioms and theorems into what we call modules. What are the theories? Okay? And then we can also mark up all of these funny arrows. Here's one. So the modules you do with a begin S module, they need a name, maybe a little bit more metadata, but you write modules. And then they collect the symbols. And then you import, or in some case, you import other modules into modules, object-oriented or modular development. And in LaTeX, where not everything is in a module, you also need a variant that kind of, that we call use module, that actually imports, but doesn't re-export. A module does re-export the imported modules, but when you're not in a module, you need a variant of that doesn't re-export. And then we kind of bunch up everything into what we call archives, which is a packaging tool to make large, like 3,000 pages of these things packaged. So what we do is we kind of have an object-oriented LaTeX with inheritance, where we keep the macros and their mathematical definitions and properties in the same place. Not all too shocking for people like you who are doing the same thing outside of LaTeX anyway. Okay? But in LaTeX, this is kind of new, and what we want to do is we want to re-implement a modularity scheme and a knowledge representation for math inside LaTeX. It changes quite drastically what you do with LaTeX. Okay? And there's more. You can do things like, say, the imaginary unit I always want to have expressed as a j or as an I, depending on what I like. There's a special treatment for mathematical structures like monoids and so on, which is kind of the record type-like treatment of theories. We use them internally and externally. That's very useful. If you want to write down group homomorphisms, you have to somehow go up on universe level. That's how we're doing it. That all works quite nicely. We have some initial support for structures and views. All the copy machine is kind of in LaTeX already. We don't quite like the syntax yet, but we're working on that. We can combine this with learner models. If you have all these URIs for the concepts explicitly marked up and harvested from then you can actually use MMT to do things for you, like model learners. And the Holy Grail, which I would like to pursue in Bonn, is actually link all of this up to Lean and Talk and all of those kinds of things, so that we can actually integrate those things and kind of use STech as something like the blueprints in in Lean, which is really what it's made for, because it's a lot more formal than just writing down LaTeX and with presentational formulae and linking them to formal theorems. Kind of, it allows deep linking. And I think that's going to be attractive. I'll answer your question in the coffee break, because there's something I want to take. They'll show you, to make all of this work, we can't just use PDF LaTeX, because that makes PDF, which is a terrible format to do anything with. So what we're doing is we're actually making HTML, and to be more specific, semantically annotated HTML. Like STech, differs from normal LaTeX by having all these semantic annotations that you don't see in the output, except if you work hard. We're doing the same thing with an HTML translation, and Dennis Müller has basically re-implemented tech in Rust, with the effect that we can make nice-looking HTML out of generic LaTeX. There's no special treatment for STech. The only thing that you need to do in STech is actually say, oh, when you're processed by RustTech, please deposit all of these semantic annotations so that you get semantic HTML. And then we take the MMT system, let it read the HTML, which you can also look at in the browser, and glean out all the formal parts. What is a symbol? What is its URI? What does it look like? And all of those kind of things. And this SHTML, we call it, is kind of what we base our systems on. Okay. And we use all of this in computer-supported education. And I have the choice now whether to give you a live demo of what we can do by basically taking the learner modeling component and the HTML-based Flexiformalization, or I can show you how this copy machine, which we know works for formal content, like copying theorems over, might actually work for copying educational stuff over. Anybody have any preferences? No, good, then I'll decide. And I'll just show you the system. Wait, that was not what I wanted. So, here's the stuff written in STech behind the scenes. And we have all kinds of formulae, in this case, formulae that you already know, and you can do things like on hover show definitions. You can recursively do that. This is conjunction and those kind of things. And you can use the formalization to actually give services. You can also let me scroll down a little bit. After a section, this is my AI course. Let me try to find the section.
Looks like a logic course to me.
That is what AI 1 should be. Namely, show people symbolic AI. Not just this, the good old-fashioned AI, not just the newfangled buzzword-compliant AI. So I misuse my power of making courses to let people learn all of AI.
I think they call it a bait and switch.
Right. So one of the things you can do after any kind of a section is analyze the section because it's fully annotated to see what are the concepts that are introduced in this section. that is automatable. By the way, truth doesn't play a role here, just structural things like was defined in a section. And then just basically add something here, which is basically review, first order deduction. And then you can see two things from the learner model. How well do I, in this case, understand what's going on here? And you can see not at all. I'm not using my own things. So for all of the concepts, the semantic stuff, we have a learner model that kind of tells us how well the student remembers, understands, and can apply. Okay, in this case, terrible for Kohlhase, right? But those are the things that have been introduced in this section, and I can actually do practice problems because we also annotate all the problems, all the quiz problems, all the homework problems, all the exam problems with what they test. The objectives, those are just basically apply natural deduction, things like that, and their prerequisites. The prerequisites kind of give us a lower bound of where these problems are useful at the earliest, and the objectives gives us when are they useful at the latest. Okay, so we can automatically put them in there. The more we have, we don't have enough yet. We have a growing pool of remedial problems here. That's one thing you can do. You can also, oh, there we go. Before a new section comes, you ask yourself a different question. Not have I learned enough from the old section, but am I prepared for the new section? So you can analyze the sections of what are the prerequisites of everything. Not what is introduced in the new section, that's going to be new. But am I prepared with the prerequisites? And we have this traffic light here that actually tells you, do I have the competencies? And again, gives you things like drill cards, flashcards, that's basically the definitional part, or quiz questions, if we have any, or homework and exam questions, and all of those kind of things, so that you can actually practice on them, which internally informs the learner model, which actually makes the interaction better. So if you actually do, I'm not sure what's happening here. If you have internal, if you do use the system, then that actually updates your learner model and directly makes all of these interactions better. The last thing I want to show you is, say, what we call guided tours. You've already seen that we get the definitions recursively, but you'll have spotted that this is the wrong way around, right? It's just like reading the index of a book, which is not what you want. What you really want is to have the professor go up to you on a blackboard. The professor knows what is new to you, and then they'll give you a mini lecture culminating at, say, this substitution thing. This is something we can do because we have enough semantics. So if instead of hovering over it, you actually click on it, you get not only all the definitions, we know of them, there are multiple courses, maybe here's from computational logic, and here's from the Platonic library at the end, but you can also generate what we call a guided tour, and I hope that this is actually coming back. No, it's not, then I'll kind of hand wave my way around it. It's basically, if you have the definitions and you know what the definienda are and you know what terms are defined terms, then you can basically say, then you have the beginnings of what we call the terminological dependency relation, right? Substitutions. Substitutions depend on various things like well-formed formulae, signatures, and all of those kind of things. And so you can have this relation topologically sorted, throw out everything that the learner model thinks the learner already knows, and that gives you a targeted explanation. Depends on the learner model being correct. If it's not, you can actually say, I don't want to see this, I can apply this, I can understand this, and I even remember what it is. And again, updating your learner model. And so we have, in this system essentially, which we're using on hundreds of students in my big AI lecture and a couple of other lectures, you have two components that are important. One is the intrinsic semantics, which we annotate using STEC, and this learner modeling thing. Plus a couple of other things that I haven't told you about yet. But those two kind of have an intense interaction that allow you to make what we think of as the beginnings of good teaching automatic. And just to conclude, truth is handled at a completely different level. You could verify this. You could put all of that stuff into theorem provers or computer algebra systems. The beginnings of that are there if we align them sufficiently, which is something I would like to talk to you about. But that's not the crucial aspect. The crucial aspect is things like topologically sorting the dependency relation and giving it to students. Or taking the learner model and customizing quiz questions or customizing your drill cards and stacks and those kind of things. And that is something you can only get by semantics. Because the learner model is nothing but a formula, a function from concepts to, in this case, 6 tuples of probability distributions for the various cognitive aspects. And then you can actually start implementing stuff. It's a nice application, independent of truth. The truth is handled by the instructor. They know the domain pretty well, and it's not that difficult that you made lots of mistakes. That's not the crucial thing. It's shaping the content such that students can understand. Having ways of shaping the content so that students can understand in a student-adapted way that also works at 1 o'clock in the night when I'm actually asleep, right? And maybe I could do it better as a brilliant teacher. But I'm sleeping. So anything that's automated is going to be good for the student. And that's, I think, what we should be after here. That's why we need formalization.